I certainly have made contributions to the topic of the workshop, but not a whole lot recently. So when I started to prepare the talk, I was really wondering, what should I talk about? So my idea then was to talk a little bit about what from hardware should programmers actually know, and to give some introduction to some concepts of specifically NISQ, because this was supposed to be the near-term keynote. And so I make the professional theoretical chemists on the audience a bit more of the, as a target audience than those people who are intensely working on quantum computing. The people working on quantum computing will probably learn about a few things that they already know, just explained in a slightly quirky way. So I will first look a little bit about what can we do right now and what is important to kind of distill from the huge information about hardware, specifically what's the big deal with errors. What are things where as a programmer you see the hardware constrictions, and then I have a bit of a proposition on the gates that we should use when looking at typical near-term chemistry problems. And then I will talk about two results from my group. One is a bit older. It's a quantum algorithm for the Green's function, and a technique that we like to call symmetry benchmarking, which actually directly relates to the gates, what gates chapter. Please interrupt me at any time. This is more... the point here is more to define terminology rather than, getting to any specific end statement. So let's think about hardware and how to use it. So when people say NISQ, noisy intermediate scale quantum technologies, a term coined by John Preskill, what they mean is that actually when you look at your favorite quantum computing textbook, that you're skipping the fault tolerance chapter, rather you directly work with the hardware that you have. And for a long time, I showed the thing on the top right. Actually, is the cursor visible here? Probably not. So I just say where things are. I play radio, which was the first computer I ever owned, a masterpiece of British engineering called the Sinclair ZX81, which had 1 kilobyte of memory, which was had a kind of very efficient architecture. But you started learning assembler basically after a month of owning it, even at age 12. And you learned how to abuse the hardware. But actually, this is probably even more advanced. Really, we are more on the stage of the Simon computer, which contains a bit over 50 relays, which is also the magic number for NISQ quantum computing, and where the hardware is really visible. So when trying to do something useful with this very simple hardware, it is quite visible what the hardware limitations are, even to the user. And even though it would be desirable to make it more fault tolerant, on this scale of hardware, the science of fault tolerance, which is error correction with redundancy, and that means substantial redundancy, is not something that we can afford to do. And I think later there will be a more forward-looking fault tolerance keynote also in this session. So I stick with this. So why do quantum computer scientists talk about errors that much, you may ask? Well, there's a couple of reasons. And actually, I think the well-posed problem is that why do classical computer scientists talk about errors so little? And this is because the CMOS logic system, where you can represent logic states as states in this type of double well of 0 and 1, is quite forgiving. When your voltage, if the x-axis here is, for example, voltage, is below some threshold we identified as 0, if it's above some threshold we identified as 1, and the circuits are set up so they naturally gravitate towards the center of the voltage interval. So only if you hop over the barrier, you produce a hardware error. And this is so rare that software errors typically come first. So in classical computing, error correction is mostly relegated to high security applications and to communication. In quantum computing, we of course deal with quantum states. So we deal with superpositions of 0 and 1, so which we can write as indicated on the right. So there is a couple of observations. First of all, there are two error channels, an amplitude error and an error in the relative phase. But also, if we now have analog errors on these parameters theta and phi, they can in principle accumulate. And if they, they do this with a square root law, if they're truly random, but there's no such thing as automatically pulling you to the center of the correct voltage interval. So they build up. Now, a small error of this amplitude, of course, always translates into a small probability of the output error. But if you make many of them, still your output error probability of your algorithm will be too high. And on top of this, hardware is on the early stage. But it's, I think, a safe assumption that even if hardware becomes a lot better, the fact that this analog property of quantum information during the algorithm, that this will stay with us until we do full error correction. Now, let's look at available algorithms for quantum computer chemistry. And you will again see later in the conference that my quantum computing colleague will now be really bored that the first natural class is based on phase estimation. So phase estimation contains the algorithmic primitive on the upper right. That is the quantum Fourier transform, which is very, very efficient because essentially the effort takes as an input the number of digits, the number of sampling points of the Fourier signal you have, and not the number of digits and not the number of sampling points. So it's exponentially faster than classical Fourier transform. It has a few quirks like gates with very small rotation angles, but it can work around. So now you can use this to essentially look at the slowest Fourier component of the unitary matrix, which is e to the minus Hamiltonian of the molecule times a time step tau. Now the difficulty here is on top that you need to load what you would like to Fourier transform into the input register of the top algorithm, which you do by calling controlled versions of this time evolution. So the U on the lower right is the time evolution under the molecule. And you need to do this in different powers and then apply the Fourier transform. This is called phase estimation. And if you put all of this together, and I will kind of touch on the main issue of implementing this Hamiltonian, you will end up with an algorithm that is very deep and skinny. So if you put out all the elementary gates, you will need a lot of them. You're quite qubit efficient. But for NISQ, where error rates are a problem, where you want to limit the number of gates so the output error has a low probability or an acceptable probability, this is unlikely to happen. So this is typically discussed for fault-tolerant quantum computing. So rather, what you use is the property of near-term quantum hardware that the most reliable operation it can do is initialization. Initialization is either based on cooling or on some measurement-based approach, but it usually has a much lower error rate than, at least a long string of gates. So effectively, rather than running this very deep algorithm, you run short algorithmic pieces in a subroutine, for example, to an optimizer. This cannot only be applied in quantum computer chemistry, but also, for example, in optimization. It's shown to be universal by Seth Lloyd, who I've just seen. So basically what you do, I've shown this on the right for work on the Green's function, not on chemistry in the traditional sense that I will explain a bit later. And I've also seen that Pierre-Luc is on the call, where essentially you give some parameters to your quantum simulator or to your NISQ quantum computer. You let it output a quantity that you can sample. That could be the ground state energy. That could be the Green's function. Then you put this in a classical optimizer and you return a new set of parameters that will hopefully lower your figure of merit, which could be the energy, which could be the free energy. And while the classical computer is working, it will, you can reset your quantum simulator, and after a few iterations, when you're satisfied, you output this. So here, at each of these pair of green arrows that are horizontal, you're resetting the quantum computer by this greatly improving your error budget. Now, when you in the first case, you need to implement an algorithm that implements the qubit, the molecule. Here, you at least need to read out the molecule. So there is one difficulty, which I think has been very well addressed by the community. So I just say this, that, you know, to lay a baseline, which is the mapping of fermions onto qubits. This is often done in second quantization. So spin down and up correspond to orbital being unoccupied or occupied. So the raising operators correspond of fermions called C dagger correspond to raising operators of qubit called sigma dagger. And what is very nice is that the local anti-commutation relations here are all satisfied. So if the indices are the same, however, if the indices are different between the fermions are indistinguishable and globally antisymmetric. Qubits are distinguishable. When I have them on my chip, I know which one is which. So the non-local symmetry relations between qubits are commutators. The non-local ones are anti-commutators. This can be accommodated either by the Gendron-Wigner transformation, which gives you phase factors and which is quite a physical transformation, by the Bravi-Kitaev transformation, which is much more efficient. And there's a couple of newer and more efficient developments, which I'm sure will be discussed later in the workshop. Now, what that means is that even though your physical Hamiltonian is always fourth order, so the Coulomb interaction has at most 4 operators in it, the actually implemented Hamiltonian can be a lot heavier because of this encoding. This is, I think, a well-studied problem, but we'll probably see progress throughout the meeting. Now, when we look at these variational algorithms, there is one kind of important distinction when we look at them in chemistry versus looking in combinatorics. So in theoretical chemistry, what we really would like to have is the ground state energy. So what we do is we start from a fiducial state, from a state that we believe is a good starting point, that is often Hartree-Fock. And then we try to find a set of gates that we can control by some continuous parameters, and where we have some guarantee that if we vary these parameters, we sample the relevant state space. Ideally, this could be a full configuration interaction. This is, however, typically not feasible. This is too many parameters. But then there are reduced sets that get us close enough so we can find a good ground state energy. And then we read out the many-body observables. So then we read out the terms in the Hamiltonian of the molecule. So when we prepare the state, we are actually never invoking the Hamiltonian of the molecule. And I think the reason for this is that this would be extremely hard. That would make the algorithm extremely deep again. So that would kind of remove the advantage that we can go from going to VQE. In combinatorics, we have the situation that I'm sketching below, is that we start from a kind of generic input state, Hadamard state, and then we are interleaving the driver Hamiltonian, which makes superpositions, which makes new states with the problem Hamiltonian, with the thing that we would like to solve. And that typically is good for the convergence of the QAOA algorithm, which is the variational algorithm for combinatorics. But it would be interesting to understand, at least I am really interested in understanding whether it would actually, what is the benefit from interleaving the driver Hamiltonian, and are there elements that we should also interleave in quantum computer chemistry? Now, let's look at error rates. So I talked to you that error is important. I hopefully convinced you about this. How are they typically measured? Well, a good community standard, and this again, you know, my quantum computing colleagues all know this, is a method called randomized benchmarking, in which you have a method that makes you mostly independent of state preparation and measurement, or SPAM errors. You really only measure the errors of the error per gate. It actually averages over a large set of gates, that in most cases is the Clifford group, which is a restricted set. It's discrete, and actually it's officially simulable. However, and for fault-tolerant quantum computing, it's actually a big deal go outside the Clifford group. In NISQ, I would argue that typically the hardest gate you make is the 2-qubit gate, and whether your 2-qubit gate is Clifford or not is not really a big distinction. It is a small distinction. So I think these numbers are fairly good predictors of performance for NISQ. There are some extensions. You can pull out more error details. And if you have no interest in hardware, then you should actually not really listen to error measures that are lower level than randomized benchmarking fidelity. You should not listen to, for example, coherence times, because when somebody tells you I have a long coherence time, you need to ask what is the time it takes your gate to make and what is the probability of errors that have nothing to do with coherence. And those all are kind of nicely taken into account in the randomized benchmarking. And well, there are more refined measures, but this is kind of definitely a good one. If you look at platforms for hardware, this is from a quantum computing study that is toward fault tolerance. We have written this for the German Information Security Office. It's public and it's in English, only parts of this plot are in German. But it shows you that if you look at a full roadmap that goes from level A to level E for fault tolerance, well, nothing goes beyond C. So we're all struggling to really do something with error correction. And this is also where the NISQ sweet spot starts. And there are some front runners, superconducting qubits, a variety called 2D transmons and ion traps. But the field is pretty dense, and passing and resorting of this field is absolutely possible. It could be that in a couple of years, this looks fairly different. Give you a flavor of superconducting qubits. I mean, this is not a hardware talk, but if you Google quantum computer, well, we are on a Google platform. Our main organizer works for Google. Otherwise, I would say use your favorite search engine. For quantum computer, you actually see this chandelier type thing on the right. This is actually the fully wired cooling systems. The qubits are kind of dangling on the bottom of this impressive structure. They are built on Josephson junction, shown on the upper left. This is this intersection between two wires. This is, if you want, the counterpart with a transistor. They're put into a larger structure shown on the lower left, which has a read-write port on the bottom and ports for talking to other qubits on the right and the left. It is sitting in a sample holder and is controlled by big electronics. Now, if we look a bit more under the hood, this is a picture from an old UC Santa Barbara sample before they moved to Google. And why I like showing this picture is that it's still open in the sense that there's no plastic on top, so you can see things. So you see the same structure that I've seen on shown below, and I've already told you that the side arms of the crosses are for talking to other qubits. So you see this is a 1D chain. So when you want to make 2-qubit gates, you can only make them between nearest neighbor. Everything else has to be put to compilation. So if you want to co-design your algorithm, you have to take this into account. Also, a side remark, this is an optical microscope picture, though the structure is not very small. If we go to the year 2021, we can see two impressive results, one by Google, one by IBM, who are both in the beyond 50 qubits level, which is the level of quantum supremacy. And this is a level where quantum computers beat classical computers at synthetic benchmarks. Actually, when you run more realistic benchmarks, you're not using the whole chip for that, but fair enough. And the progress there is always limited by gate errors, not by qubit numbers. And at IBM, at Google, you see on the upper right, you see a new generation of what I've shown on the last slide. You have cross-shaped qubits. They are nearest neighbor coupled. The coupler is now adjustable. At IBM, you see what they call the heavy hexagon layout on the left on the bottom, which has a bit fewer highly connected qubits, which has to do with how they make their 2-qubit gates. And again, if you need to make a simulation, this influences the overhead, your compilation, your hardware-aware compilation will have. The qubit gates here can be made fairly fast, and they reach gate errors that are about 1%. 1-qubit gates are a lot faster, but state preparation and measurement error is reasonably substantial. If I look at ion traps, the other front runner, this is an entirely different system. It's based on on metal electrodes with this blade shape shown on top. They're now working also on chips. It's sitting The counterpart to the chandelier is the big optical table you see on the bottom. And they typically are in a string type setup in the currently most successful experiment, but the community is just getting 2D arrays to work with very similar performance. So they actually, even though these are 1D strings, within the string, they have long-range connectivity because they work by they're connected by collective modes. So the optical picture there is a bit misleading. They work on 2D surface traps. I think 10 years ago already people said that 1D traps where you have one string are dead. This was clearly exaggerated. But 2D traps then also give a different connectivity between substrings. The clock speed is a bit lower, but the error rate is also very, very low. So depending on whether, I think for fault tolerance, these are on an advantage. The low clock speed and the relatively low readout make NISQ occasionally inconvenient, but this is also very much a moving target. But clearly, when you try out one of these NISQ algorithms on a superconducting quantum processor and on an ion trap, different things take different amounts of time. Now, there is results about learning how to live with the error when you have some idea of the error. One technique that has been nicely shown by IBM, that is shown on the left, is called Richardson extrapolation. Essentially, when you know that everything decays exponentially, you can extrapolate back. You can interpret your measurement results a lot better, and also use this for getting a better reading on your quantum chemistry result. Or this on the right is a result from HQS, where also I was participating. When you have some errors, they work like additional gates, so you're naturally simulating disorder. So some understanding of the error model can actually make your chemistry simulations a bit more efficient. And I think one important thing is to get the right level of granularity of this understanding. You can also ask, which gate set should I actually use for compiling my algorithm? Now, when you open a textbook, such as Nielsen Chuang, what they're telling you is that, well, the most natural gate set is you do all single qubit relations, SU2, all relations of the Bloch sphere, for which you need 2 rotation axes. And ideally, you use C0 or the unitary XOR. So you're flipping the target qubit if the control qubit is in state 1. Now, one thing you realize, and this is shown with this hand drawing on the upper right, is that XOR is equivalent to controlled Z. Simply by Hadamard on the target qubit, you can swap them around. So we should really, whenever we talk about 2-qubit gates, talk about classes of gates that are equivalent up to single qubit rotations, specifically because single qubit rotations are also really cheap. Sometimes on some architectures, you also see the I-swap gate, which is kind of an interesting beast. It's shown on the lower right. This is in the basis of 00011011. So this swaps 0 and 1, which means on the 0, 0, on the 1, 1 state, it does nothing. And a swap gate in itself is actually not an entangler. If something is not entangled, if A and B are not entangled, then B and A are also not entangled. But the extra minus I factor that is coming in with the swap, that is actually crucial. And you can show, as is in the block above, that by local Z rotation, so the RZ is a rotation, single qubit rotation, by a swap that doesn't change entanglement and an I swap, you can get the CZ gate back. So I swap is actually a perfect entangler. And I would also like to advertise this way of thinking of connecting perfect entanglers with non-entangling gates. And so this is crucial, and I'll come in the next slide why we're doing this. Now, there is a whole science on classifying entangling gates. There's nice papers by Zhang and by Machlin from about 20 years ago. And for NISQ, the typical currency is that 2-qubit gates have a much higher error than 1-qubit gates. So paying attention to your 2-qubit gates is important. This is, again, very different from fault-tolerant quantum computing and topological quantum computing, where we typically compile into Clifford gates at the T gate, which is a single qubit gate that is non-Clifford. And that one is most expensive, and that is how you should count the hardness of implementing something on a fault-tolerant quantum computer. Now, a bit more on hardware, because why do different people offer different gates? Well, that has to do with the physical interaction between the two qubits. There is the Ising interaction. That was a German guy. I pronounce him in German. If you exponentiate this by the correct angle, you do e to the I alpha z1, z2, you get the controlled z. If you have the xy interaction shown on the right as exchange interaction, so xx plus yy, you're naturally getting an I swap if you apply it for the right time. And there is a work by Mike Geller's group showing that under a set of natural approximations called the rotating wave approximation, there's hardly anything else. So these are actually probably the most important 2-qubit gates for a lot of platforms. However, my wonder, I have to run those interactions for a very specific time. I have to solve the time-dependent Schrödinger equation for a specific time to get the I swap and the CZ. Why am I restricting myself to these times? And this is a very valid question, because nobody forces you to. And here is a recent result from the Open SuperQ Consortium, where for the QAOA algorithm, we have actually compiled continuous set of Ising type gates and shown in the middle how the conditional phase phi depends on a physical parameter called the detuning. And by calibrating this efficiently, we can natively get not only e to the I alpha z1, z2, like in the upper left here, but all alphas. And by this, we were able to go really deep in the QAOA algorithm, because we could encode a gate that the compiler needs directly in hardware. And in fact, the alternative to this would be the piece of algorithm shown on the upper left, which is 2 CNOTs and a single qubit phase gate, which is also quite attractive because it turns out single qubits phase gates often come for free. You're doing them essentially virtually. But it's 2 different CNOTs, and that gives you the error, 2 gates worth of error, whereas this only gives you 1 gate worth of error. And we, in a study that we are about to write up, we have actually compared those 2 strategies, and under generic parameters, you see a difference in fidelity shown on the right. And actually, all you really need to see here is that the bar on the right only has negative values. So in most cases, the strategy done by direct calibration wins over the strategy of compiling this into 2 CNOTs. Now, you can take this idea a lot further, and you can ask yourself, can I actually directly compile gates between 2 qubits, between more than 2 qubits, such as the Toffoli gate, which is an important algorithmic primitive, or something we've done with Pierre-Luc, the I-Fredkin gate, which is a controlled I swap, which is also needed for a couple of fermionic algorithms. And indeed, you get some more complicated waveforms. And I think an important step now is to find out, is that actually worth it? Will the final benefit of compiling this directly outweigh the effort of calibrating those waveforms? And we could go one even further and make synthetic couplers shown on the lower right from a paper that we've written with Marius Schöndorf, which is a coupler that essentially natively implements a 4-body interaction. So that has Pauli Z gates on 4 different qubits in a product. I mean, it does so in the sense of an effective low-energy Hamiltonian, but this could also give us a shortcut of implementing complex gates in one shot. And I think this is worth carefully benchmarking, because, of course, this comes off the price of more complicated hardware. Now, there has been an earlier work by the IBM group that follows kind of this idea of directly using elements that are sitting in the hardware. It's work by Kandala, where they took a entangling interaction and added single qubit gates on top of it to sample a good state space for quantum computer chemistry. And if you take this to its extreme, which it hasn't been taken to in this, you can just say, oh, if I can just recalibrate my entangler so I reach the right states, I do not need to understand how those states are reached. the existence or the reachability of relevant states may actually be enough for using this type of hardware efficiently. And I don't care to understand what my VQE gates are doing. I just care about the output. In fact, if you look at how gates are designed, what we're doing during gates, this is mostly the same procedure. Maybe this slide is a bit too detailed and also too slow. So what we do when we optimize gates is we essentially do the same thing. We have a variational loop to make gates better and better. And if you want calibrating gates with variation, to put in a variational algorithm is probably one variation too many. So what I'm advocating here is that rather than compiling a VQE ansatz, let's directly synthesize our variational parameters into waveforms that lead to well-reachable states. And that could be a lot more efficient in using the limited hardware that we have. We have not quite invented this. There are encouraging results in the area of quantum optimization by Santoro's group, where they've actually shown that they can find annealing schedules that have a very flat plateau in the middle blindly without really knowing the Hamiltonian spectrum. There are hybrid optimization schedules coming out of the University of Maryland, and there is an application of these kind of more natural controls of a quantum computer coming out of Sherbrooke, and this is probably not a complete listing. We have contributed to this also. We have looked at QAOA, our combinatorical brother, where we have shown that you do not really never switch off the driver Hamiltonian, and in fact, with just one driver Hamiltonian and a single qubit gate, you can do everything you want. One thing that helps here, which gives rise to the plot on the lower right, where essentially the brown area tells you, here you are really safe in working with this limited hardware. One thing which is very good is even if your hardware doesn't implement your gates perfectly, you don't care, because at least small deviations can be accommodated by simply slightly changing the parameters of your parameterized circuit a little bit. And by this, as I said, you do not need to implement the gates perfectly. You need to reach the right set of states. So I'm close to the end, and I could either end here or at least briefly go over software topics. Tom, what should I do?
Well, we have 7 minutes, and I see 3 questions in the chat. How long, if you've got like maybe give another 2-3 minutes on software topics, and then we'll go to
Okay, so then I would just like to highlight further things that could hopefully be discussed further and be even less detailed and more too fast than I have been now. And one thing is going from molecules to materials, because we know from Phil Warren Anderson that a solid state material is not just a giant molecule, and it contains, you know, Avogadro's number of atoms, and even polynomial overhead there is forbiddingly high. And one paradigmatic model for this is, of course, the Hubbard model. Now, my PhD was in solid state theory, and let me just say out loud, there is no material in the periodic table that is completely described by the Hubbard model. The Hubbard model is phenomenological, but of course, it is a very good approximation to many situations. I recently saw a paper that claimed to do material science and really solved the Hubbard model, and no. And one thing that I would like to highlight is that all the work that we've done with Pierre-Luc is that in chemistry, we're looking at the ground state energy of a molecule. What is actually the right thing to look like at the Hubbard model? And I would say it's the self-energy. So it is the energy that a single particle sees by the presence of the surroundings. We typically do not, we typically need at least the self-energy, because the energy of the Hubbard model itself doesn't say a lot. It's, again, not describing a real material. On the other hand, we also do not really need more. The Hubbard model ground state is full of entanglement. But for determining the phase diagram, as shown on the upper right here, we really want to see what single particle observables are doing. So one thing we are pursuing still in my group, and see our PhD student Gino Bishop on the call, is to work at quantum algorithms for the self-energy. Unfortunately, I mean, there are variational principles, which I don't want to go into detail because I've obviously prepared too much material. However, it's way more complex than the ground state energy. It, for example, has frequency dependence. So the methods that you can use to compute this typically involve a mix of variational methods. So it's good. There is a variation principle. But because it's a complicated function, you typically have a blend of phase estimation and variational calculus. And the rest I would actually skip. That would be way too technical. So you can ask me about symmetry benchmarking if you want. So as a summary, as a take-home message, I think when you look at NISQ, let's quote a Bill Clinton campaign slogan. Those were happy times in American politics. We just didn't know it by then. It's the fidelity stupid. So we are often looking at qubit number, but currently the main avenue for realizing better algorithms is clearly fidelity. I think we should explore the best use of hardware by having some understanding of the hardware we are doing, and let's not get stuck to approaches that are historic or to approaches that will work in the far future. Let's efficiently use the hardware, not have too many layers of embedding. And I think a good discussion topic can be how to actually describe hardware restrictions for user without having them to have 5 years of experience. And in this Hubbard model, we related this to the variational cluster method. And I think another thing that probably everybody here is aware is that before you should go to a quantum computer, you should really dig in classical computational methods to compute the right thing and only to delegate to the limited quantum computer what you absolutely cannot do classically. I realized that I talked way too fast, but I'm now happy to listen to your questions. I'm in full screen mode. I don't see you, but I am trusting Tom that he will now sort questions.
Yeah, okay. So we've got about 2 minutes left. So I'll just briefly, I guess I'll start off. Barbara, you had a question. Do you want to speak it out?
Wait, yes. Oh, well, of course, you were covering a lot of territory, which was interesting. Well, you mentioned randomized benchmarking as sort of a method that was sort of good for capturing, noise. But it's, we care about entropy increase, for these variational circuits, and RB doesn't care about whether I'm doing an over-rotation or whether I'm, doing some stochastic thing that introduces noise. So my question was, is there room for better benchmarking methods or other methods specifically for variational optimization?
So I would think that the principle of randomized benchmarking, the randomization of this would at least be able to cover some misinterpretation of some wrong rotation, in the sense that because you have Y gates and then Y+1 inverting gates, if they all have the same phase error, for example, that would be felt because you are making the error Y times and then you're undoing it 1 times.
Sure, yeah. I mean, you can capture coherent errors, but the idea of variational optimization is that if you do an over-rotation, but you do it systematically, then you optimize yourself out of that. So
that's true. Yes. So so what we are advocating, and which was the slides I skipped over in an already over full talk, was a method how you are just checking how much you are violating the symmetries you absolutely would like to have. So, for example, if you want to stay in a subspace with a fixed number of excitations, then you can check, am I dropping out of the subspace, which would be a fatal error. Within the family of randomized benchmarking, I believe it's possible to also get some information of systematic versus random errors, but I'm not completely sure.
Thanks. Yeah.
Okay. So I think maybe we'll just take one more question. I apologize to Alana. I've maybe let this run a little bit too long, but we'll be like 2-3 minutes late. But I guess there's a question from Mohan Saravar in the chat. Mohan, do you want to unmute yourself and speak, or I can otherwise just speak it out if you don't do that?
Sure. Yeah, I can do that, Tom. Thanks. Frank, hi. My question is, so the work with continuous gates for variational problems is really interesting. Do you know of any work where you've shown or people have shown that you can actually generate a useful set of states that way? So QAOA, the circuit version is nice in the sense that there's some guarantees that at least with increasing number of layers, you increase the approximation ratio. Similarly, are there any nice guarantees with the continuous gates?
You can look at reachability. So if you do truly continuous gates, then you need to have your controls general enough so you reach the full set. And there is, in optimal control theory, some heuristics, but I think it hasn't been fully translated yet. How much time and how many parameters you need to truly, reach the quantum. So the quantum speed limit depends on the number of parameters. So if you have a given time, you need enough parameters, and then you also have a guarantee that you can reach all states. So it's not quite there, but elements of this are there, and this is something we're interested in understanding better.
All right. Thanks, Frank, and thanks for a great talk. And thanks, Mohan, for the question as well. There's another question by Lin about how the variational self-energy algorithm works. But thing is, I think you didn't really have so much time to go over that. Maybe we'll move to the next speaker, and Lin and Frank, maybe